The bottom row of gold beads on the Pythabacus can be associated with groups of elements in a set. Each bead, when counted or touched, inputs an element in a group. For example, I touch this bead and that bead and that bead. I touch 4 beads, and that inputs an element in these columns, which represent the groups. Each column represents a group. And so each time I count or touch the first bead, I will input an element in the group. Now, I can change the numeral defining the element from 1 to 2, and now when I touch or count a bead, it will input the 2. So now I have 2 subsets of elements. A subset defined by the numeral 1 and a subset defined by the numeral 2. So, now we can explore how multiplication on the Pythabacus is related to these groups composed of the elements in the set. Okay, so to explore multiplication on the Pythabacus, first we will click the leftmost bead and click the right arrow key to reset the triangle of beads to the against the right post. Now I'm going to click the up arrow so that I can have a 1 defining the elements, and I'm going to count 3. 1, 2, 3. Click it to 0. I'm going to click the third bead and reposition it against the left post. Now I'm going to change the defining numeral to 2, and I'm going to count 5 of the beads. 1, 2, 3, 4, 5. And I'm going to click the 5th bead and move it a little bit toward the middle. And if I click the leftmost bead in the group, move it a little bit to right, I can reveal a rectangle. And now this rectangle, as we can see over here, if we count the beads, we'll find that there are 15, which is the solution to the math operation demonstrated, as we can see over here, with this arithmetic statement, 3 times 5 equals 15. And this bottom 15 here in the addition statement then represents these 15 beads, which are all the pairs of these elements, the group of 3 and the group of 5, I can make a pair of 1 and 2. How many pairs of 1 and 2 can I make? Unique pairs are possible between these sets of elements, and we will see that that will be the product, we call the outer product, of 3 times 5, which will equal 15. Now, I'm going to click the rightmost bead in the rectangle, push it over to the triangle against the left post. And now I'm going to continue my count after 5 to 7 over here. So I'm going to display the numeral 2, because I'm continuing now with the 5 count to 7. So the numeral 2 will still be defining those elements. So I got 6, 7. And you can see there are two twos inputted in the first 2 columns. And then I'm going to click the third bead and press the right arrow to see that I get a line of beads which is 1 times 5. And so I have 5 beads here, which actually represent the possible pairs of this single 1 defining element and the 5 twos that are defining elements. And 1 times 5, of course, is the number of pairs of 1s and 2s that I can compose. And we can see that that 5 shows up here in the addition statement. So I have 5, which is now the outer product between these 2 subsets of elements. And now, the 16 here is the sum of the inner products of these 2 groups. We have 2 different elements represented by the numerals 1 and 2, and so we can make a pair 1 times 1 for each of these. And here in the red you can see the multiples 1 and 1 for the inner product of these groups. And we sum all of these and that gives us 2. Now it happens that the base of this arithmetic operation will be 8 because I did not continue counting when I got to the 8th bead over to the 9th and 10th bead. I went back to the first bead. So that's how you establish the base in the math operation. So in this case, it's base 8. So the multiple of base 8 is the sum of the inner products times 8. So I got 2 times 8, which now gives us 16. And 16 plus 5 equals 21, which of course is equal to the math operation demonstrated by the Pythabacus 3 times 7 does equal 21. Okay, so now I'm going to click this rightmost bead and click the left arrow and push that back over against the triangle against the left post. And I am going to now continue counting my second count with 2's. And so I'm going to touch that bead and add a 2 in the third column. And so now I have 3 times 8 as the operation, because I have the 2's, as you can see here, include these 5 and these 3, which makes 8. And 3 times 8, as you can see here, is 24. Then you can see the second rows of 2 equals the 1's in the first row. And so that's telling us that the number of 2's is exactly equal to the base, 8. And so now that means there's no outer product, because there's only one set, the set of elements defined by the 2, beyond these groups here. So there's no outer product, so that we have 0 for the outer product. But if we look now at the inner products, we have an inner product for each of these. So we have 3 inner products, and of course 3 times the base 8 does give us 24. Okay, so let's continue counting by 2's, the second count. And so we're going to continue, but first I'm going to take the rectangle here, and we're going to click the right arrow. Not too far with it. Push it back a little bit so we can see it there. Now we're going to continue counting the second count, inputting the numeral 2 to demonstrate the second count. So we got to 8 here, and we're going to continue beyond the base 8, and we're going to count 3 more in the second count. So here we go. 8, 9, 10, 11. Push these out slightly. Now, we have an extension of groups, and there's 2 different extensions. We have the extension of groups where in the first row we have 1's, and the extension of group where in the first row we have 2's. That gives us 2 extension of groups, and there's 3 in each extension. So now we get an outer product between these 2, and we'll get 3 times 3 equals 9, which is, you can see here, 9 beads representing the outer product of those 2 extensions of groups, and also given here and now. And of course we still have the 3 times 8, which gave us 24, so we have 24 plus 9 equals 33, which equals the solution of the mathematical operation demonstrated. 3 times 11 does equal 33. And so you can see in this way you can understand the multiplication on the Pythabacus as being equivalent to the inner and outer products of groups of elements from 2 subsets. In this case, we can see defined by the numerals 1 and 2.